Hello, I'm Francesco Leoni, and this presentation will be about preliminary finite element assessment of residual stresses in the similar aluminum steel but welded joints produced with the hybrid metal extrusion and bonding technique. In recent times, good experimental results were found for the similar aluminum steel but welds produced with the I-bond technique. So far, numerical models were developed for this process only to study the thermal field that arises during joining of aluminum butt welds, while numerical investigations were still missing for dissimilar metal joints produced with this novel welding technique. The purpose of this work was to develop a numerical model for this new process in order to predict the stresses evolution during dissimilar welds. In this work, the process parameters were chosen according to what will be used in planned experiments of this similar aluminum steel butt joints. In this presentation, I'm going to start with a brief summary of the I-bond process to make you familiar with it. Afterwards, I will show you the simulations that were performed, and finally the results and some conclusions. Let's now talk about the process. The hybrid metal extrusion and bonding process is a novel welding technique that is under development in Trondheim, Norway. The method utilizes continuous extrusion as a technique to enable filler metal addition. Bonding is reached through a combination of oxide dispersion, shear deformation, surface expansion, and pressure. In the figure, you can see the HIBE pinpoint extruder in operation with its main parts. This slide shows some applications of the I-bond technique. As you can see, the technique is versatile and can be applied to join dissimilar and similar metals in different configurations. In literature, you will find some reports on the soundness of these joints. In this slide, examples of cross-sections of a butt weld obtained with the I-bond process are reported. The butt welds were obtained for different groove width between the plates, showing how the technique can be well suitable for different needs. In fact, one advantage against friction stir welding is the possibility to have a gap between the materials to be joined without undergoing problems of lack of filling. To give you some quantitative information, the table below shows a benchmark of the I-bond process against gas metal arc and friction stir welding based on comparison of tensile test data obtained for 4 mm thick aluminum butt welds. Let's now see how the tool works. As previously said, I-bond process is based on the principle of continuous extrusion and allows joining to be performed using aluminum filler metal additions similar to that done in gas metal arc welding, but without any melting involved. The figure highlights the core parts forming the I-bond pinpoint extruder. In the situation of butt welding, the two plates to be joined are divided from each other by a fixed space, so that an I-groove forms between them. During welding operation, the pinpoint extruder shown in figure moves along the joint line at a constant travel speed, while the rotating pin with its moving dies is submerged between the plates. This enables the extrudate to float downwards in the axial direction and mix with the base metal in the groove under the condition of high pressure and severe plastic deformation. Metallic bonding between the filler metal and the base material occurs as a result of these two contributions, along with oxide dispersion. By taking into consideration the mass balance involved, the extrudate flow rate can be adjusted in such a way that the groove between the plates is filled with solid aluminum in a continuous manner. In this slide, you will see the principle of continuous extrusion, which is behind the wire feeding system used for filling the material in the I-bond process. Finally, in this slide, with this animation, you can see the tool in operation. This should help you to visualize better the rotating and stationary parts, forming the core part of the machine. Let's now see the welding parameters investigated. The three welding conditions shown in table were investigated. They were chosen according to planned experiments where the effect of the welding speed on the joint soundness will be investigated. The materials joined were aluminum alloy 6082 and structural steel 355. The filler material was a wire with a 1.4 mm diameter of aluminum alloy 6082. Let's now see how the simulations were set. First, the geometry was created using the software pattern. Then a neutral file containing the node's coordinates and the boundary IDs was exported to be used as input to the WeldSim finite element code. The length and the width of the plates were 500 and 100 mm respectively. A backing plate were also modeled to account for the heat conduction with it. These simulations were set considering these thermal boundary conditions. In the table you can see that different heat transfer coefficients were set between the plate and the steel backing and between the weld path and the steel backing. Moreover, also air-cool effect was considered. The shown material properties, function of temperature, were set for the two materials. Elastic-plastic behavior was considered. In order to run the simulations at 3 welding speeds, the heat input had to be assessed, and this was done considering a heat generation model developed for butt welds of similar aluminum joints. This model considered the welding conditions and calculated the corresponding heat generation generated by the interaction between the tool and the workpiece, and by the filling of the hot material. This model was written in MATLAB. Once the heat input Q0 was calculated, the value was sent to the finite element code that assessed the thermal history and finally the thermal and residual stresses. Let's now see the results obtained. The thermal history is plotted for 3 welding speeds. At the top there is the aluminum, where the heat is transferred much faster than in the steel, which is placed in the bottom. As can be seen, the temperatures are relatively low, and this is in accordance to experiments, where melt of the parent material is not observed. This confirms the validity of the heat generation model employed. These graphs here are a comparison between the temperature evolution considering a cross-section of the plates taken in the middle length of the welds. As the welding speed increases, the temperature drops, but not as much as it would be observed in fusion welds. This is because here the heat input also changes with the welding speed, while in fusion welds it can be set constant. Moreover, a narrower thermal field is observed for higher welding speed. Longitudinal thermal stresses are here shown. No great differences between the different cases can be observed in these plots. In this slide, the deformation before and after unclamping of the plates are shown. Finally, the longitudinal residual stresses are plotted, considering a cross-section in the middle length of the plates. Here, a difference between the 3 cases can be observed. In particular, it can be noticed how the welding speed affects the width and the amplitude of the stresses. It is noticed that increasing the welding speed brings to a narrower plasticized zone with a higher stress magnitude. And now let's finally draw some conclusions. Finite element analyses were performed to study the thermal stresses generated during the similar joining of the novel welding technique I-bond. From previous works, it was found that heat generation depends on both the welding speed and the rotational speed of the tool. The heat generation model developed and calibrated for aluminum butt welds were employed to estimate the heat generation during joining of aluminum to steel. Once the heat values were determined, thermomechanical finite element simulations were run for the 3 welding velocities, and the thermal and residual stresses were obtained and analyzed. From the model, it was observed that the welding speed has effect on the plasticized zone near the weld line. And this is physically reasonable because the temperature field is lower for higher welding speed, leaving cold a larger portion of the base material, which therefore does not undergo plastic deformation. Experimental investigations are planned, and measures of residual stresses will be compared to what was found in the present preliminary work. Thank you for your attention.